Let us look at some operations on NumPy arrays now. So let's look at them from an example standpoint so it becomes easier for us. Imagine if I've created a NumPy array like this. It's a one-dimensional array with 4 elements, 1, 2, 3, 4. And if I say, and this NumPy array is stored in a variable called a. Now if I say a plus 1 here, if I say a plus 1, here 1 is a scalar, right? It's not a vector or it's not an array, right? So if when I'm adding a scalar, what happens is this 1 gets added to every element here. So 1 plus 1 becomes 2, 1 plus 2 becomes 3, 1 plus 3 becomes 4, 1 plus 4 becomes 5. So when you do a scalar addition to a matrix, so if you say 1, 2, 3, 4, which is actually an array, to this if you add 1, right? This is an array. To an array like this, if you add 1, this 1 is added to every element of the array, and what you get is this, right? So this is called the scalar addition. Similarly, if you have this array a, and if this operator is nothing but the exponent operator, right? This operator is nothing but the exponent operator. So when I do a star star 2, what happens is it takes each of the elements of a and computes the square of the element, because exponent 2 is nothing but square, right? So 1 square is 1, 2 square is 4, 3 square is 9, 4 square is 16. So this is also a element wise operation. If you notice, all these operations are element wise because they operate on each element individually. Now similarly, let's take a slightly different operation between arrays now. So what is our A? Our A was 1 to an array which is like this. It's not a list, it's an array, right? This is a NumPy array, not a list. Okay, now I'm saying B is np.ones 4 plus 1. So what happens to B I'm saying is np.ones 4, which means it creates an array of length 4. Now I'm adding 1 to it, which means all of these values become 2, right? All of these values now become 2. Now I'm saying A minus B. So what happens when I do A minus B? What happens is 1 minus 2 is minus 1. 2 minus 2 is 0. So what it's doing is it's doing element wise subtraction, because both A and B are arrays right now, and hence it's doing an element wise subtraction. 3 minus 2 is 1, 4 minus 2 is 2. Now if I do A star B, remember here A and B are both arrays. When I do A star B, what happens is it does component wise multiplication. This is called element wise multiplication. So it multiplies 1 with 2 to give you 2, 2 with 2 to give you 4, 3 with 2 to give you 6, and 4 with 2 to give you 8, right? So this is basically addition and multiplication of arrays. This is basically addition and multiplication of arrays of same size, right? Now let's look at a slightly different variation. There is something called, so when I say np.diagonal 1, 2, 3, 4, what do I get? I get basically a diagonal matrix which is 1, 2, 3, 4, 0, 0, 0, 0, 0, 0, 0, 0, 0. Right? This is what I get. I get a matrix like this, a 4 cross 4 matrix, which has 4 rows and 4 columns. I get a matrix like this, right? Where the diagonal elements are 1, 2, 3, 4. Let's assume this matrix is C. Now, if I do C star C, what happens? It multiplies this matrix with itself. It multiplies this matrix with itself. So some of you, or most of you, I'm assuming, have learned how to multiply two matrices. You basically take the first row, multiply with the first column and sum it up. Similarly, you take the first row, second column and multiply it up, so on and so forth. And when you multiply these two, what you get is a matrix like this. You can actually try it manually and see it. The final matrix that you get here is 1, 0, 0, 4, 0, 0, 0, 0, 9, 0, and 0, 0, 0, 16. This is what you get if you do C multiplied by C. And this is simple matrix multiplication. This is simple matrix multiplication that most of us would have learned in a 10th grade or in a 11th grade, typically, right? So very simple matrix multiplication. Now I can do the same matrix multiplication using two ways. One is C multiplied by C, or I can say C dot C. Because typically in mathematics, in linear algebra or matrix algebra, we actually use the dot notation to multiply two matrices, right? Or two vectors in some cases. So C dot C can also be used. The result is exactly the same. Okay. So this is matrix multiplication. Now let's look at comparisons. Now imagine if I have two NumPy arrays. My first numpy array is 1, 2, 3, 4. My second numpy array is 5, 2, 2, 4. Now, if I say a double equals to 2, I'm trying to compare a and b. What it returns to me is now an array of length 4 where it does element-wise comparison. Is 1 equals to 5? No, and hence it is false here. 2 equals to 2? True. 3 equals to 2? False. 4 equals to 4? True. So it is doing an element-wise comparison when I do double equal to. Similarly, I can use other operators like greater than, a greater than b. What it gives me is 1 greater than 5? False. 2 greater than 2? False, because it's equal to. 3 greater than 2? Yes, it is true. 4 greater than 2? False. Right? So this is how you can do it. So there is another thing called element-wise array comparisons. Right? Now let's look at it. So now I have 3 arrays here. Right? What I'm doing here is if you do np.array equal a and b. Now what it does, so this function is different. We are not using the double equal to sign here. We are saying array equals. Now, is a and b equal? No, they are not, right? Because these two elements are different and these two elements are different. So it will return false. What about np.array equal a and c? So a and c element wise they are the same, right? They are exactly the same element wise. So it will return true. So if you want to compare whether all elements of two arrays are equal or not, the best way is to use array equal. Okay. Now let's go and look at some simple logical operators. Again, very, very straightforward. Suppose if I have two numpy arrays, here I'm saying that the data type is Boolean, right? I'm giving a vector or I'm giving a list of ones and zeros, 1 representing true, 0 representing false. Now I can do basic logical operations like logical or logical and using these commands in NP or using these functions in NP, right? Very, very simple, nothing very fancy here. Okay, having said that, now let's go and look at some slightly more interesting mathematical functions. Now here I'm saying a equals to np.arrange 5, which means I get an array which looks like this. I can say np.sin a. Then what it will do is compute sine theta, the trigonometric function sine theta, right? It will the trigonometric sine to each of these values and returns me an array. Similarly, I can compute log, right? But remember, log of 0 is not defined and hence it returns minus infinity, right? Log of 1 is 0, log of 2, log of 3, log of 4, right? So you can apply functions like sine, log, or exponent. Exponent basically means e power x. Okay, e is a special mathematical symbol which is called the base of natural logarithm. If you don't know that, it's okay. We'll anyway encounter e a lot of times in probability statistics and in machine learning in general. So we'll relearn this concept. So it's basically doing e power x for each of the values. And e power 1 is 2.718. Okay, so you can apply mathematical functions like sine, log, exponent because they all are available in NumPy automatically for you. And it does element-wise operations here. Okay, now let's look at what happens if you're trying to. So this is a very fun thing. Imagine if I have a NumPy array of 0, 1, 2, 3, right? Because I'm saying np.arrange 4. To this, if I try to add another NumPy array like this, okay, it makes no sense, right? Can you add these two? Can you add these two arrays? You can't because they're not of the same size. Because you could add this. What about the rest of these two? There is nothing to add them with. So when you try to do this, it says operands could not broadcast together with shapes. So one of them has a shape of 4, the other has a shape of 2. And hence I'm not able to add them. So it gives you something called a value error when there is a shape mismatch between them, right? So now let's look at some very basic commands that you can do. So we learned about reduce functions, right? Reduce functions take a list or an iterable data structure and it returns some value of it. So here also we have some reductions. For example, let's look at some of these very simple reductions. Suppose if I have a NumPy array and if I say np.sum, it sums up all of these elements and returns us the sum. Similarly, if I have a matrix here I have a matrix which is 1, 1 and 2, 2. Now I can say this matrix is called X. Now I can say x.sum axis equals to 0. When I say axis equals to 0, what it does is it does column wise sum. When I say axis equals to 0, it does column wise sum. So what it returns me is now an array which is 3 cross 3 because it is summing these columns, right? If I say axis equals to 1, what happens then? So now I have an array which is 1, 1, 2, 2 And when I say axis equals to 1, it does row-wise sums, right? It does row-wise sums. So it sums 1 and 1, it gives 2, 2 and 2, it gives 4. So it returns us. So when I do an axis-wise sum, x dot sum axis equals to 1, axis equals to 1 means it's a row-wise sum, axis equals to 0 means it's a column-wise sum, right? So now here I get 3, 3, while for column-wise sum, I get 3, 3, right? If I sum these two, I get 3. If I sum these two, I get 3. So column-wise, so if axis equals to 0, I get this. If axis equals to 1, I get this, right? Now let's look at other simple reductions. So for example, if I want to find the minimum element, right, between all of them, the minimum element is 1. Whatever the maximum element, it is 3. There are two other very interesting functions called argmin and argmax. Let me explain what they are. So I have an array like this now, 0, 3, 2. This is at index 0. This is at index 1. These are indices. These are indices. And this is my array. So when I said, what is the minimum value? It returned me 1. This is the minimum value, right? Now, if this is the minimum value, the index that it is at is called the argmin. Because, again, we'll see this when we learn optimization. It's a mathematical notation. Argmins are used in optimization a lot. Okay, so that's where the terminology argmin comes from. Argmin basically says at what index in this array is my smallest element. So if you say x dot argmin, it returns 0. What about the maximum element? This is the maximum element. And what is the index it is at? It's at 1. So which means this becomes the argmax. Right? So if you say x dot argmax, you get 1 because at index 1 you have the largest element. Right? So argmax and argmin are important. Anyway, we'll revisit them when we learn optimization later in this course. Right? Similarly, you have some of these very, very simple functions like all. You can say np.all. If all of them are true, it returns true. If any one of them is false, it returns false. Similarly, np.any, what it does is if any one of them is true. So any is like logical or, this is like logical and. Intuitively. So if any one of them is true, it returns true. Right? You can use the same any and all for other things. For example, look at it here. Here I've created np.zeros 50-50. Right? So what am I creating? I'm creating a matrix of size 50 rows and 50 columns where all the elements are 0. Now I can say np.any a not equal to 0, which means is there any element which is not equals to 0? No, and hence it's false. Similarly, you can put any Boolean operation here. You can say np.all a equals to a. Of course, a is equals to a because every element of a is equal to every element of a, and hence it returns true. Right? Let's look at slightly more interesting and more complicated stuff here. Okay. So let's assume I have this array A, which is 1, 2, 3, 2, B 2, 2, 3, 2, C 6, 4, 4, 5. Now look at this. When I do this, I get a fairly big. So when I say A less than equal to B, what happens then? A less than equal to B returns me an array which is this less than equal to this? Yes, true. Is this less than equal to this? True. Is this less than equal to this? True. Is this less than equal to true? True. Right? And I'm doing logical operation of that with B less than equal to C. Okay. Is B less than equal to C element wise? True, 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 true. And when I do a logical AND of both of these, what happens? I get true, 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 true. And now I'm saying dot all. Of course, all of them are true, and hence you get a return value of true. So we can construct very, very complex examples like this. Again, based on what you need to do. So literally in one line of code, you have tested whether every element of A is less than equal to B, and every element of B is less than equal to C or not. Literally in one line of code, you have done the whole thing. Okay, which otherwise you would have to write a for loop comparing them, again a for loop comparing these two and stuff like this. Now you could achieve all of that literally elegantly in just one line of code. Okay, now let's look at some very simple things. Suppose if I have two arrays, suppose I have an array like this, 1, 2, 3, 1, right? If I compute x dot mean, which gives me the average value, which is 1.75. Similarly, I can compute median. Now, if you do not understand what mean and median are, we explain them in the exploratory data analysis chapter. Okay, so don't worry what you do if you don't. They're basically mathematical operations. Similarly, y is now an array. Y has 1, 2, 3, and 5, 6, 1. This is my y, right? Now, if I say compute the median of y, right, and axis equals to -1. So when I say axis equals to -1, it means the last axis. Now I have two axes here, right? My axis 0 means columns. My axis 1 means rows, right? My last axis is nothing but my rows, right? Now when I say find the median, so what is the median of all these three numbers? Median of all these three numbers. So I could, even if I had said +1 or -1, it's the same thing. It means by rows, right? What does this mean? When I do the mean of all of them, so the median of all of them is 2. The median of all of these is 5. Median is the central value. So you can compute median on matrices using the access command. Similarly, there is something called a standard deviation. Those of you who do not know what is standard deviation, please check out our videos in the exploratory data analysis chapter where you'll understand them. And again, it's a mathematical operation. It's a statistical operation to be precise. Okay. So these are NumPy helps you do all of these things. Now let's go and look at some data. So here I have a very simple data. Here in the same folder, I have a file called populations.txt. Okay. So this population.txt has 4 columns of data. My first column is the year. My second column is the population of hares or rabbits. Hare is nothing but another word for rabbit, right? Lynx is a type of wild cat, right? And carrot, the population of carrots, the number of carrots that are available. Let's assume in a given forest, these are the numbers for every year. These are the numbers of rabbits, numbers of wild cats, number of carrots. Remember, your rabbits or hares eat your carrots, and your lynx, which are your wild cats, eat your hares or rabbits. Okay, so whenever you see this number like 77.4E3, what it means is it is 77.4 into 10 power 3. What is 10 power 3? 1000, right? Into 1000. So this is called the scientific notation of storing numbers. So this is 77,400, right? So whenever any number is written E3 or E4, what E3 means is it represents multiplied by 10 power 3. That's what it represents. Okay, very simple. Now I have this table, I have this file. Now let me see how I can load this file and do some simple operations. Okay, now in NumPy it's very simple. I just have to say np.load text populations.txt. This whole file is loaded now. Now if I try to print the data, it is actually stored in a NumPy array for me, right? So each row becomes a row in my table because it's in my array literally, right? Now what I can do here is, so the transpose operation is an interesting operation. If you have a matrix like this, let me show you the transpose operation. If you have a matrix like this, 1, 2, 3, 4, 5, 6. Let's assume this is a matrix A. Now when I say A transpose, this is how it's written mathematically. In the program, it's written A.T. What it does is, it takes the rows and converts them into columns. So I took the first row and I converted it into a column. I took the first row, I converted it into a column. Similarly, I'll take the second row, I'll convert it into a column. Okay, so A transpose is basically taking the rows and converting them into columns. Now remember, look at it. This is basically 2 rows and 3 columns. So this will become 3 rows and 2 columns. That's what transpose means, right? So now I can create 4 variables called year, hares, lynx, and carrots as d.transpose, right? Now if I say print year, I get an array of all the years. Okay, now let's try to operate on this data, do some basic operations. Because my first column, remember my first column of data is year, sorry, let me just write it, year, hares, right? My lynx, I believe this is the spelling, right? Okay, and carrots, right? Now what I'm doing here in this function, what I'm doing here is I'm saying data, take all the rows. That's what I mean here. Take all the rows, but take from, so this is column 0, column 1, column 2, column 3, right? This is what my table looks like. So it's saying take all the rows, but take from first column onwards up to the last column. So it's basically taking this subset of my matrix. It's discarding the year. So what I have in my populations variable is the actual populations of all these three species of plants or animals. Okay, this is for carrots, this is for lynx, and this is for hares. Now if I want to do some simple computations on it, suppose if I want to find the standard deviation of these populations, I can say populations.standard deviation axis equals to 0. When I say axis equals to 0, what happens? It computes by column, not by row. By column basically means this column represents hairs, this column represents lynx, and this column represents carrots, right? So, and hence that's how you get it. Now, if I want to find, so let's ask a question: which species has the highest population each year, right? Then what do I want to do? Every year, these are the three populations, right? So this is for year 1900. These are the three populations. Year 1901, so on and so forth. So if I do, and this is index 0, index 1, index 2. Now I want to find out which of these three organisms or plants or animals have the highest population in a given year. What can I do? I can simply say argmax, np.argmax populations axis equals to 1. So what happens as soon as I say axis equals to 1, it's going to operate row wise. So it's going to take this row and say, and we are saying argmax, right? So it says which of these three is the largest value. So here this is the largest value, right? This is the largest value and the index of that is 2, so it will return 2. So what I get finally is basically an array like this. See, this is the question: which species has the highest population each year? Now I've just used my axis equals to 1 and argmax. These are all stuff that we learned, and now we are applying it to data, right? Very, very simple example to answer a real world question. This is a fairly genuine question, right? In NumPy, there is a very, very important and interesting concept called broadcasting. Let me explain you what broadcasting means. Okay. Suppose I have an array like this: 0, 0, 0, 10, 10, 10, 20, 20, 20, 30, 30, 30. Now, when I add this array, so this is a matrix, right? This is a matrix. This is it has 4 rows and 3 columns, right? 4 cross 3. To this, if I add one more array, right, which is again 4 rows and 3 columns, what do I get? This is equivalent to adding these two is equivalent to the same thing. It's equal to adding these two, right? It's exactly this. I've just copied it. What is the final value that you get? The final value you get is this. See, because what it does an element-wise addition, right? It does an element-wise addition. So if you add these two, it is same as this is same as this. This is exactly same as this. Okay. So adding these two is same as these two. Exactly. Just copy paste. But overall, it's equivalent to, because I'm doing element-wise sum, right? So you take this 20 plus 1. So this value should be 21. So it's element-wise addition. Now comes the fun part. This is the obvious trivial part. Now comes the fun part. Okay, imagine if I have a NumPy array like this. Now I can add this to another NumPy array which is just 0, 1, 2. Broadcasting, basically what it does is, now it tries to adjust the second array. What it tries to do is it replicates this array so as to fit this size. Because the number of columns here is 3. Here also the number of columns is 3. Here the number of rows are 4. Here the number of rows is 1. So what it will do is, it will simply, so this addition will be equivalent to, it will replicate these number of rows. It had only 1 row initially, right? So it will create 3 more rows and then it will add up everything to result in the same thing. Right? Elegant. Now there is a third way. Imagine, see, if you notice, it is this, when you replicate it thrice, you exactly get, these 3 rows are exactly the same. So what if I just have this row and I just have this column? Sorry, I just have this column and this row. Now when I try to add it, and if I say replicate this 3 times and replicate this 4 times, when I say replicate this 3 times, what happens is it creates this new matrix. This is the original matrix. It's now replicating the same thing 3 times. When I say replicate this 4 times, it replicates this 4 times now. And now when I add these two, I get the exact value. We'll see this with some code example. This concept is called broadcasting. This whole concept is called broadcasting in NumPy. It's very, very unique to NumPy actually. Okay, now let's take an example. Okay. I'll change this code slightly. So there is this function called tile, which will pile up these tiles, right? It's literally like these tiles being piled up. Okay. So let's look at it. Let's look at an example, right? So here I'm creating a NumPy array 0 to 40 with intervals of 10, which means now it creates 0, 10, 20, 30. This is the array this part creates an array. It's a one-dimensional array, right? Now what I'm saying here is replicate this 3, 1, which means replicate this 3 times. Replicate this 3 times in terms of rows. So when I replicate the same thing 3 times in the rows, what happens? I get this. I'm replicating 3 times in the rows. what I get is this. In the column space, this 3 basically means replicated 3 times. So this 3 is the same as this 3. This 3 times I'm replicating. This one says replicate this only once, right? And now what I get, my np.tile, when I print a, what I get is exactly this. What I get is exactly this. Now let's play with this and change it a little. Okay, let me change this code also a little so that it becomes easier for us to read it. Okay, let me just, so that I'm trying to make this more readable for us. Okay, so let's print this. Okay, this is what I get because I'm replicating. Again, just to quickly repeat myself, I have my original array which is 0, 10, 20, 30, and it's saying replicate 3 times in the rows. So I've replicated it once, twice, thrice. In the columns, just replicate it once, so it's there only once. Now let me change it slightly. What happens if I just change this to 2? Sorry, not 21, 2. Okay, now what happens? Now I get a slightly different array. Okay, so now let's see. My original array was 0, 10, 20, 30. This is the power of the tile function. It basically tiles things up, like putting one tile on top of other. Now here I'm saying replicate this array that I have 3 times in the rows. So replicate it 3 times in the rows. Once, twice, thrice. But in the columns also replicate it twice. So which means now columns it's replicated once and replicated twice. This is the replication of twice in the columns, right? And this is the replication of columns 3 times here. So you can use tile to construct more and more complex tilings. See what happens in tiles. You put one tile on top of other tile on top of other tile, next to another tile, next to another tile, etc. Right? Exactly, that's what we are doing. Right? So now let me go back and change it to the original one because the rest of the code follows that line. Right? Now again, so this is my original array. Now if I transpose it, what do I get? I get 0, 10, 20, 30, 0, 10, 20, 30, 0, 10, 20, 30. If you notice, this is exactly what we have here. 0, 10, 20, 30, 0, 10, 20, 30, 0, 10, 20, 30. And I've created this using, so and I'm saying A equals to A transpose. So this becomes my new A, right? This becomes my A matrix. Now, if I say, let's create a new array, which is B. My A is exactly the one that we saw earlier. My B is 0, 1, 2. If you notice, what is my B? My B is exactly this. My B is exactly this. This is my A and this is my B. That's what I'm defining it. I'll keep coming back to this diagram. Okay. Now if I say A plus B, what happens? Now remember, when I say A plus B, what's happening here is A is already of size 3 columns, right? I have column 1, column 2, column 3, row 1, row 2, row 3, row 4, right? And this is column 1, column 2, column 3. When I try to add these two, right? Because this matrix is of a much larger size and the columns at least are matching. The columns here, there are 3 columns here, there are 3 columns here. What it internally does is it replicates this 3 times like this. It replicates this, 4 times because I have 4 rows and it adds them up and this is the result I get, right? So let's see the result that we get when you do that. All I'm doing here is I'm taking my A, my B is this, I'm saying A plus B and I get what you expect, which is exactly this result, right? Now let's do something much more fun. Now so we have seen this case, right? So there are 3 cases here. This case is the obvious case. It's basically element-wise addition. We have seen this case. Now let's look at this case. So I'll create this as A and I'll create this as B and now I'll try to add and show you that broadcasting, this concept is called broadcasting in Numpy. I'll show you that broadcasting works as we expect. There is a small catch here. Let me explain you that. Okay, so I'm saying A is a Numpy array which is 0, 10, 20, 30, right? Now it's of size 4. Now there is this new function which says np.newAxis. Now remember, this is a one-dimensional array. Okay, I need to convert this. I need to add a new axis here. I need to convert this to a 2D array, right? So when I say A equals to A, all the rows and np.newAxis, and when I create this, what it creates now is actually, see, earlier it is a one-dimensional array. Now it gets converted to a 2-dimensional array, right? With 4 rows and only 1 column. Because that's what my data is, right? Now if I try to print A, my A looks like this. My A from becoming a one-dimensional array. So when I do this, A is one-dimensional array. But as soon as I do this, my A becomes a two-dimensional array. My A becomes a two-dimensional array where I have only 4 elements, but in 4 rows and 1 column. Now, since I've changed this to an array, to a 2D array, since I've changed this to a 2D array, I can do A plus B. And it will give you the result that we expect. So what we've done here is, here we have a 1D array. We converted this 1D array to a 2D array. And then to this 2D array, we added this. Then everything works out. Now what happens if I don't add the 2D array? If I don't have this step, what happens? If I don't have this np.newAccess, what is this literally doing? It's converting from 1D array to 2D array. If I don't do this, this addition will not work. It will say sizes don't match and hence error. Okay, so whenever you want to do this third type of trick, whenever you want to do this third type of broadcasting, you have to convert this 1D array to 2D array, take the 2D array now, add it to this, and then your whole broadcasting works as you expect. That's a small catch there. It's very, very important. If you just try this code without doing the np.newAccess, and it will fail. Now let's go to some simple array manipulations. Okay. So there is an operation called flattening, a very important operator actually. We use it extensively in data science. So here I'm creating an array which is 1, 2, 3, 4, 5, 6. It's a 2D array, of course, right? When I say a.ravel, R-A-V-E-L, what it does is it converts this array into this two-dimensional array into a one-dimensional array, such that it first reads the first row, 1, 2, 3, puts them here. Next, it reads the second row and puts them here as one contiguous array. This is called flattening, because you're taking a big square and you're flattening it into a line, right? That's why it's called flattening. This operation is called flattening, right? Very, very simple operator, nothing very fancy, right? Similarly, we looked at transpose. So we know how transpose works. And if you do Ravel after transpose, you get a different matrix, obviously, right? So we understood transpose earlier itself. So no worries there. Now let's look at it. If you want to reshape a matrix, this is fun. What is our matrix? 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6. This is our matrix. And it has 2 rows and 3 columns. I'm printing the shape and I'm printing the matrix itself. Now, if I say b equals to a.ravel, what happens now? My b is 1, 2, 3, 4, 5, 6. Now I can again do b.reshape 2 cross 3. Then I will get my original A matrix here. So Ravel is a function to flatten, and reshape is another useful function, which if you give it a flattened value, it will reshape it into other values. As long as, remember, here in a 2 cross 3 matrix, I need 6 values. And if there are 6 values here, it will work. Otherwise, it will give you an error. Okay, very, very simple. So reshape is also a very, very useful function. Now comes the fun part. Now, remember what I've done. B is now nothing but a raveled or flattened form of A, right? And B is been reshaped slightly. Now, if I say B0, 0 equal to 100. Okay, so what am I doing? I'm changing this value to 100. If I print A now, my A's value also is changing, because what Numpy does internally is Numpy is storing the whole matrix internally for both A and B the same. Internally, it's storing in the same memory location. So whenever you change the memory location, it is not copying. It is not copying the values of A into B. Sometimes it does. That's what you have to be slightly aware of. But in this case, what's happening here is because Numpy wants to optimize memory storage, because the data inside is still the same, right? So whether you're flattening it or whether you're reshaping it, Numpy stores that data internally in some format. Okay, so it doesn't care. So when you change your B value, your A's value, so I'm printing A and my A value also has changed, because both A and B are pointing to the same location in memory. But beware, reshape may also return a copy sometimes. Like for example, in this case, right? You have a Numpy array of zeros of 3 cross 2, and now you're transposing it, reshaping it and things like that. When you change B, your A hasn't changed. So sometimes you have to be very, very careful here. This is one type of mistake that happens a lot when you're reshaping values. Okay, now let's look at so we saw how to use new axes, right? To add a new axis to your data. So now let's look at it. Okay, here I have a Z is my Numpy array, which is 1, 2, 3, which is a one-dimensional array. If I want to convert this into a two-dimensional array, all I have to do is this. We saw this new axis example, right? A while earlier when we were doing broadcasting examples, right? Similarly, now comes Now comes the fun part. Okay. Suppose if I want to arrange, suppose I want to construct this matrix. Again, this is of, it has a shape of 4 cross 3 cross 2. It's not a two-dimensional matrix. It's a three-dimensional matrix. It's a three-dimensional matrix with 4 cross 3 cross 2, which means it has 4 matrices of sizes 3 cross 2. It has 4 matrices. Okay. And each matrix is of size 3 rows and 2 columns. That's how we can think of three-dimensional matrices. Okay, tensors, as I told you earlier. Now I can arrange all these values. So now I'm saying np.arrange. How many values do I need to fill a 4 cross 3 cross 2 matrix? I need 4 into 3 into 2. So that's about 24 values I need. So I'm saying np.arrange 24. So it's going to arrange all of them into one array like this. 0, 1, 2, 3, 23. And now I'm saying reshape them into this. So now it's reshaped them, and when it typed the shape value, it says it has 4 matrices of 3 rows and 2 columns each. This is how it exactly looks. Plotting a three-dimensional matrix on paper is hard, right? But I can go and change a specific value. For example, here I'm saying that I want to change for the 0th matrix, for the second row and the first column, what is the value? That's what I'm trying to answer. Or I can allocate a value here. So let's try to find out, right? Now here we have 4 matrices. So what is the size? 4 cross 3 cross 2. We have matrix 0, we have matrix 1, we have matrix 2, we have matrix 3. And each of these matrices has 3 rows. Row 0, row 1, row 2, and column 0 and column 1. So when I say A021, it goes to the 0th matrix, second row, and first column. The value is 5. So that's what it printed. This is how you understand indexing in high dimensional arrays or in multidimensional arrays. Okay, so again, not very hard, but you have to be slightly careful. Now let's look at it like this. Okay. Now if I say np.arrange 4, what do I get? I get 0, 1, 2, 3, right? Now if I say a.resize, right? When I say a.resize, what happens is it resizes it to 8 elements, but it concatenates the rest of the elements with zeros. Now here is a type of bug that often occurs when we're using resize arrange, because we do this a lot of times in machine learning and data science. Now if I say b equals to a, and if I try to resize a now, it will not let you do it. Okay, so the error in this case would be this is all right? Because you're trying to resize it to a larger element, so it just adds zeros there. That's perfectly all right. But if you have referenced, or if you have another variable pointing to the same thing, so in A, you have these values, right? 0, 1, 2, 3, all zeros. Now, if I try to have B also assigned to it, and if I try to resize it now, it says cannot resize an array that references or is referenced by another array. Okay, that's a value error. So you have to be careful if there are 2 variables or if there are 2 names which are pointing to the same location, resizing it will create errors. So we learned about try catch, so we need to catch those errors. Now let's look at some simple sorting stuff. Very, very important, because we sort data a lot actually in data science. So here I have my matrix 5, 4, 6, 2, 3, 2. Okay, that's what I created here. Now I said np.sort axis equals to 1. What does axis equals to 1 mean? Axis equals to 1 means row wise, right? So I want to sort this row, and when I sort this row, what happens? I get 4, 5, 6. When I sort this row, what do I get? 2, 2, 3. Okay, that's what is the result. Okay, or if I want to sort it, so here I'm sorting it and returning it to a new variable, right? If I want to sort A itself, I can just say a.sort instead of np.sort here. Okay, what this does is it modifies A itself. Now after doing a.sort, if I say A, it will sort A and it will store the sorted value back in A itself. Okay, now there is something called fancy indexing, which is actually very, very interesting idea. Again, used extensively in data science. So imagine if I have an array like this, 4, 3, 2, 1, right? This is my array. And now I'm saying np.argsort. I'm not saying sort. So argsort, what it does is, so these are my initial indices, 0, 1, 2, 3. Now first it sorts this internally. Okay, when it sorts this, what do I get? 1, 2, 3, 4. Okay, this is the sorted. But when I sorted it, what happened? The indices changed. So what happened? The second index came here. I'm just copying this index here. What is the index of 2? 3. So the 3 value came here. What is the index of 3? 1. right? What is the index of 4? 0. So when I say np.argsort, what I get is basically the positions of the indices after sorting, right? And now if I say aj, because j is now my argsort, my resultant value of argsort. So now it will get my first a2 value. What is a2 value now? A2 value is 1. Next it gets a3 because this is j, right? Because this is j. This is my vector j. Now when I say aj, it uses these values as indices, right? So a2 will be 1. What about a3? A3 is 2. It printed 2. Similarly, a1 is 3. A0 is 4. Right? So argsort is very, very important. And I recommend you play this with larger examples. Since you have this source code with you, I recommend you play with this and understand how all of these functions are useful, especially broadcasting and argsort. Most of these NumPy functions, we use them extensively. Trust me, we use them a lot in data science and machine learning.